In the previous lesson, we have discussed about some basic rules in probability, and in this lesson, we'll be discussing about some more advanced rule in probability. The main goal of today's lesson is to be able to compute probabilities associated with different complex events, and we should also be able to identify the difference between independent events and mutually exclusive events. And we'll also define with example what is conditional probability. Before discussing about any topics, let's first look into some notation that we commonly use in probability. So to indicate probability that an event A will occur, we use this symbol and we call that probability of A, and we call that symbol probability of A given B, which basically indicates probability that A will occur given that B has already occurred. So this is probability that A will occur given that B has already occurred. And this is the probability of A and B, and we also use probability of A intersection B, and sometimes we simply write probability of A V. So that means probability that A and B both will occur. And then this is probability of A or B, or we can also use probability of A union B, that basically indicates the same thing, and that indicates probability that A or B or both will occur, meaning like A or B will occur, or both can also occur. Let's now start with the discussion of our first concept, which is independent events. So we call two events independent if the occurrence of one doesn't affect the other. As for example, here we have two events A and B, and now if the occurrence of A doesn't affect B, or if the occurrence of B doesn't affect the probability of A, then we call these two events independent. Let us clarify that with an example. Suppose you are throwing a coin and rolling a die. Then we have defined the event A as head will appear in the coin and B as die shows 1. Now the question is, if we say we already have 1 in the die, whether that affects the probability that head will appear in the coin. It doesn't, right? Therefore we call these two events independent. And for independent events, something also happened. Let us discuss with this probability. So for the coin, we already know that probability that head will appear is 1 over 2, right? Now, according to the definition of the independence, we are telling that the probability of head shouldn't depend, since these two events are independent. It doesn't depend on whether we have 1 or not in the die, right? Therefore, this probability also should be 1 over 2. Therefore, these two things are same, right? So we can tell probability that A given B is equal to probability of A. Therefore, the main takeaway from this slide is that the independence means given something doesn't affect other, doesn't change the probability of other, right? And mathematically we say probability that A given B is equal to probability of A. Let's now see how do we define conditional probability, meaning what is the probability that an event will occur given another event has already occurred. So let me explain that with this Venn diagram. Suppose we have the information that B has already occurred. Now what is the probability that A will occur? So here basically we are interested to calculate that, like what is the probability that A will occur given that B has already occurred. Now let's see how we can do that. So here the right circle, so this is the event A. So that right circle, any area inside this right circle indicates that B has happened. Now if we already know that B has happened, what is the probability that A has happened? Now here, if you notice, if B happened and if it happens in that area, only in that area, only in this, if something happens only in this region, only in that case A also can happen, right? So if say B happens and if it happens in that area, then A cannot happen, right? So we are interested to the probability that what is the probability that A has happened given that B has already happened. That means we have to define, we have to find what is the probability that something inside this area will happen given the whole things to the right side, that means to the right circle, that means the B has happened, right? So how we can calculate that? So here then on the numerator we will take the common part of A and B, that means probability that A intersection B has happened, this part, given the whole circle to the right, that means given the B has already happened, right? So therefore we can define the conditional probability, that means the probability of A has occurred given that B has already been occurred. We read it as probability of A given B. And how do you define that? We take the common part of A and B on the numerator, and on the denominator we take the probability that B has already occurred, right? And that basically give us the conditional probability of A given B. And in that case, the B, basically the probability of B cannot be zero, because if the probability of B becomes zero, then this equation become undefined. Let's now discuss about the general multiplication rule. So general multiplication rule is nothing but rewriting our conditional probability equation in a different way. So here from the conditional probability from the previous slide, we already know that, right? Probability that A given B is basically the probability that A and B on the numerator, and on the denominator we'll have the probability of B. We already know this from the conditional probability from the previous slide. Now from this equation we can basically write that, right? Probability of A and B equal to, we just have to multiply this with that, right? So probability of A given B times probability of B, or interchangeably like that basically means the same thing. We can also write probability of B given A times probability of A. So these two basically indicate the same thing, right? And this is true for like whether the two events are independent or not for both cases. So from the previous slide, from the general multiplication rule, we know that probability of A and B equal to probability of A given B times probability of B, or probability of A and B equals to probability of B given A times probability of A. So these two basically indicates the same thing, right? Now earlier we have discussed about our independent events, and we have defined like if two events are independent, that means if the occurrence of one doesn't affect the probability of other, then we can write that probability of A equal to probability of A given B, right? Or we can also write like probability of B equal to probability of B given A. So this is true for independent events, right? And now we'll see how for the independent event our multiplication rule is, and we will discuss about that in the next slide. From the general multiplication rule, we already know that probability of A and B equal to probability of A times probability of B given A, or probability of B probability of B times probability of A given B. So from the multiplication rule, we already know that, right? Now for independent event, we have also discussed earlier, like for independent event, probability of B given A is basically same as probability of B, right? And probability of A given B is same as probability of A. Therefore, these reduce to probability of A times probability of B, right? These two basically reduce to probability of A times B. It basically reduces to probability of A times probability of B, because if these two events are independent, then that's same as probability of B. Therefore For independent events, if two events A and B are independent, then for independence event we can write that probability of A and B is same as probability of A times probability of B. So now let's look into some examples. So here we have two person, James and Olivia. James is 55 years old now and Olivia is 35 years old now. So probability that James will be alive for next 10 years is 0.72 and Olivia will be alive for next 10 years is 0.92. And we have assumed that two events are independent. Now we have to find the probability that both will be alive in the next 10 years. So we'll see in the next slide how we can calculate this probability. So now to calculate this probability, the very first thing we have to ask whether these two events are independent or not. And we have already assumed that these these events are independent. That means lifespan of one person doesn't affect others. We have already assumed that. Therefore, for independent events, that is the formula that probability that A and B is equal to probability of A times B. That means probability that both will be alive is equal to the event to the multiplication of their individual probability. That means probability that James will be alive for the next 10 years, which was like 0.72, and probability that Olivia will be alive for the next 10 years is 0.92, right? And the multiplication of 2 is around 0.67. That means like the probability that Olivia and James both will be alive for the next 10 years is 0.66, right? Let's look into another problem. So in that case, we have to draw two cameras from 100 cameras without replacement, and we have 10 defective cameras in the lot. Now we have to calculate the probability that both of them will be defective. And in the next slide, we will see how we can calculate this probability. So initially, how many cameras we have in total? So we have 100 cameras, and out of 100 cameras, we have 10 defective cameras. Now for the first draw, like what is the probability that first one will be defective if we randomly like draw one cameras from this 100 camera? So it will be 10 over 100, right? Because initially we have 10 defective cameras and our total number of cameras was 100. Therefore, the first one will be defective. Probability that the first one will be defective is 10 over 100. So this is the probability that first one will be defective. Now in the next slide, we will see what will be the probability that second one will defective, given that first one is already defective, right? Now we already have the information that the first camera we drawn was defective. Now how many cameras we have? Now we have 99 cameras and we have 9 defective cameras because we already have the information that first one was defective. Now what is the probability that second one will be defective given the first one is already defective? So now how many defective cameras we have? We have 9 defective cameras. And how many total cameras now we have? We have 99 total cameras, right? Therefore, the probability that second one will be defective given the first one is defective is 9 over 99, right? Now, the question is whether these two events are independent or dependent. Now, let's see. So, for the first event, the probability that it was defective was 10 over 100, which is like equivalent to 0.10, and probability that second one will be defective given the first one was defective was 9 over 99. So these two numbers are not equal, right? Therefore, the probability changing here, and which basically indicates these two events are dependent event, right? So now for the dependent events, what was the multiplication rule? So the rule was the probability that A and B both will occur is probability of A times probability of B given A, right? So the probability of both defective is then 10 over 100 times 9 over 99. So that give us the final result, which is about 0.009. That means the probability that both of the cameras will be defective is 0.009. Now we'll see what do you mean by mutually exclusive events. So we call two events mutually exclusive if they cannot occur together. As for example, here, say we have two events A and B. So we call A and B mutually exclusive if there is nothing in common in between these two. That means they cannot happen together. And say if there is nothing in common in between A and B, then the probability that A and B will be 0, and the probability of A given B will also be 0, because if B happens, then A cannot happen, right? So the probability of A given B will be 0, and similarly probability of B given A is also 0, because if A happen, then B cannot happen. And two events are not mutually exclusive if there is something in between these two is common. As for example, here you can see like there is some part of A and B which is in common, therefore they are not mutually exclusive. Earlier we have discussed about multiplication rule. Now let's look into addition rule. And first we'll discuss about non-mutually exclusive events. So for non-mutually exclusive events, or the general rule is like the probability of A or B equal to probability of A plus probability of B minus probability of A and B. Now let's see how basically we have this formula. So here we are interested to know probability of A or B. So now what we are doing, we are taking the probability of A, then we are taking the probability of B. So therefore we are considering this part twice. We are considering this part twice, but that we cannot do that, right? Because that's a repetition. So what we have to do, then we have to subtract this part. And what is this part? This is basically probability of A and B, right? Therefore, the formula is probability of A or B, probability of A or B equal to probability of A plus probability of B. Then we are considering, since we are considering this twice, so we'll subtract that once, minus probability of A and B. Now for non-mutual, sorry, now for mutually exclusive event, what happens? So for the mutually exclusive event, there is nothing in common in between A and B. Therefore, the probability of A or B equal to simply the sum of the individual probabilities. That means probability of A plus probability of B. Now with an example, let's try to see how we can calculate probability for non-mutually exclusive event. So in that case, consider a standard deck of cards, and for a standard deck of cards, we basically have 52 cards. 13 of them is hearts, 13 dice, 13 spade, and 13 clubs. So we define events A as drawing a king, and define event B as drawing a heart. Then the question is whether these two events are mutually exclusive or not. And they are not basically mutually exclusive, right? Because there is one card which is king of hearts, which is both a king and both a heart, right? So now in that case, we would apply the general addition rule to calculate the probability. Therefore, the general addition rule is probability of A or B equal to probability of A plus probability of B minus probability of A and B. Therefore, you have to know the individual probability first, and then what is the common. So how many king we have? We have in a deck of 52 cards, we have 4 king. Therefore, the probability that if you draw a card randomly, it will be a king is 4 over 52. And how many hearts we have? We have 13 hearts, right? So therefore, the probability of hearts would be 13 over 52. Now, what is in common? There is one card that can be like king of hearts, right? That could be king and that could also be hearts. Therefore, the probability that it would be king and hearts is 1 over 52. So the final probability that if you randomly draw a card, it will be king or heart is this probability plus this one minus this probability, right? So finally that give us 4 over 13. So if you randomly pick a card, then it will be both king or sorry, it will be king or heart, or both is like 4 over 13. Now we'll see with an example how we can calculate probability for mutually exclusive events. Suppose you went to a clothing store to buy some clothes, and you are interested to calculate the probability that this pant will be too tight or too loose, and we have the individual probability that probability it will be too tight 0.30, and the probability that it will be too loose is with 0.10. Now the question is we have to find the probability that it would be too tight or too loose. Now the very first question that we have to ask is whether these two events are mutually exclusive. Now, is that possible that a pant will be both too tight or too loose at the same time? It is not possible, right? So therefore these two events are mutually exclusive. It cannot there cannot be anything which is common, right? So now how we can calculate the probability that probability it will be too tight or too loose? So it would simply be the sum of the individual probabilities, right? Because there is nothing in common, they are mutually exclusive. Therefore the probability would be like sum of the probability that it will be too tight plus the probability it would be too loose, and that gives us 0.40. So if you randomly buy pants, it will be too tight or too loose with probability 0.40. We have already discussed about mutually exclusive event, but let's look back. So here two events are mutually exclusive. Two events A and B are mutually exclusive. That means there is nothing in common in between these two. Therefore, the probability that A and B equal to 0, because both cannot happen since they are mutually exclusive. And in that case the probability of A or B would simply be the addition of the individual probabilities. That means probability of A plus probability of B, and the probability of A given B and probability of B given B both are 0, because if A happen, B cannot happen, and if B happen, then A cannot happen, right? So yeah. So throughout this lecture so far, we have used many symbols, and I want to discuss about them further so that the symbols become very clear to all of us. So suppose we have two events A and B. So event A indicates the person is taking college classes, and B, he is under age 30. Then the probability of A and B, so what does that basically indicates? So that indicates that the person is under age 30 and he is also taking college classes, right? So probability of A and B here indicating the person age is under 30 and he is also taking college classes, right? So let's look into some more symbols. So here we have the same events. Event A, somebody is taking college classes, and events B, he is under age 30. Then this symbol probability of A given B equal to 0.45 indicates the person who is under age 30 is taking college classes with probability 0.45, meaning like 45% of the person who are under age 30 is taking college classes. And what does this symbol means here? Probability of B given A equal to 0.60. So that's basically indicate if the person take the college classes, then the probability that he will be under age 30 is 60%, right? So far we have discussed about many formulas that we have used, and we might be confused. So let's see everything together and summarize. So if two events are mutually exclusive, that means if there is nothing in common, then uh, we have to use this formula. So if two events are mutually exclusive, then the probability of A or B equal to their sum of their individual probabilities. That means probability of A plus probability of B. But if two events are not mutually exclusive, that means if there is something in common in between these two, then probability of A or B would be probability of A plus probability of B minus probability of A and B. We have to subtract like what is common in between A and B here. And for independent events, if A and B are independent, then probability of A and B is simply the multiplication of their individual probabilities. So probability of A and B would be probability of A times probability of B. And if two events are not independent, then probability of A and B would be probability of A times probability of B given A, or probability of B times probability of A given B. So let's discuss about some common mistake that often we do, and we often like confuse independence and mutually exclusive events. So two events are mutually exclusive if there is nothing in common in between these two. As for example here, A and B, so there is nothing in common in between these two events, so therefore they are mutually exclusive events. And in that case, the probability of A and B would be zero, and the probability of A given B is also zero, because if B happens, then in A cannot happen, and the probability of B given A is also zero, because if A happen, then B cannot happen. And on the other hand, for independence, so for independence, basically the happening of B doesn't affect the probability that A will happen, and so probability of A given B is same as probability of A, and the probability of B given A is same as probability of B, and probability of A and B will simply be the multiplication of the individual probabilities, meaning probability of A times probability of B. So this is really very important, so think about them carefully before applying like Swiss formula you should use in this case. So now with an example, try to determine whether two events are independent or not. So here we have the probability of A equal to 0.5 and the probability of A given B equal to 0.3. So are these two events independent? So here the probability here 0.5 is basically not equal 0.3, right? So therefore these two probabilities are not equal, therefore they are not independent, because we know that if the two events A and B are independent, then probability of A equal to probability of A given B, and in that case that is not true, right? Therefore we can conclude that A and B are dependent, they are not independent even. That means knowing B occurred change the probability of A. Let's look into some more problem. So here we have probability of A equal to zero point 0.5 and probability of B equal to 0.3 and probability of A and B equal to 0.2. So are A and B independent? So here probability of A times B would be like probability of A, which is 0.5, and the probability of B, which is 0.3, and that equals 0.15. So and we have like probability of A and B 0.2 from here, right? That's already given. So in that case zero point 0.2 is not equal to 0.15, right? So therefore these two events are not independent, these two events are also dependent, right? Because if they are independent, then here like this probability will be equal to this probability, but in this case this is not true, right? So let's look into some more examples. So in that case as well, we have to determine whether two events A and B are independent, and we already know that two events A and B are independent if probability of A and B equal to probability of A times probability of B, right? So let's first try to understand what does the table basically means. So here this table means, what does these values in the table means? So here means somebody is male and he also likes red color is with probability zero point 0.2. Somebody is female and like the red color with probability zero point 0.2. Somebody is male and like blue color is with probability zero point 0.3. And if somebody is male, he doesn't like the yellow color at all, and therefore the probability here is 0. That's the result from the table. I don't know what that really is. And for the female, if somebody is female, that she will like red color is with probability zero point 0.2. She will like blue color with probability zero point 0.2, and she will like yellow color with probability zero point 0.1. And so now what are the results that we have? What are the individual probabilities that we have? So in that case, the probability of red would be like sum of these two probability, sum of this column, which is like 0.4. So the probability of red would be 0.4. Then the probability of male, the probability of male is like 0.5. The sum of this column, the probability of male is 0.5. Then to determine whether the events are independent or not, we need that quantity, right? So the probability of red times probability of male, what would be this probability? So what is the probability of red? The probability of red, the probability of red is 0.4. Probability of red is 0.4. Probability of male is 0.5. So the multiplication of these two would be 0 0.2. So the probability of red times the probability of male is 0 0.2. Now we have to also find the joint probability, right? That means the probability of male and red, and the probability of male and red, probability of male and red. So this part, right here, which is 0.2, right? So the probability of red and male is 0 0.2. So now we have to compare this result with this result. So here we have the probability of red and males equal to probability of red times probability of male, right? Because these two probabilities are same. So therefore we can tell that liking red and being male are independent events since these two probabilities are equal. So I guess now it is more clear to all of us like what we basically mean by independence. So if two events are independent, then we also know this formula, right? That probability of A given B would be equal to probability of A. So from this table, let's justify that whether this is true. So here from this table, we have that probability of male is zero point 0.5 here. Probability of male is 0.5 here. Then we also need this probability, right? Probability of male given red, and how we can determine that. So that's basically equal to probability of male and red given red, right? That we know, we already know about this formula. So how we can find this? So first we have to find probability of male and red. So probability of male and red is 0.2, and then probability of red, we also need probability of red, and probability of red is like 0.4. Therefore we have these quantities now, and then to calculate probability of male given red, what we need to do, we just need to divide that with this, right? So 0.2 over 0.4, and that basically give us 0.5. So now we can see like probability of male equal to probability of male given red. So these two are equal. Therefore from this as well we can say like being male and liking the red color are independent events, right? Now let's use a different table, and from this table try to see whether liking grade and being male are independent events or not for this table. So here the probability of red and male versus probability of red versus male for this, like what are the information what we have, like the probability of red and male here, probability of red and male here is 0.3, and then probability of red, what is the probability of red here, probability of red is zero point 0.4, then probability of male is 0.5. So the multiplication of probability of red times probability of male is then finally 0.2. So in that case we can see like these two probabilities, like probability of red and male is not equal to probability of red times probability of male, right? So therefore these two are not independent events. And from, we can also use another formula, this formula to justify, right? And check whether probability of male given red is equal to probability of male. So here probability of red given male, what is probability of red given male, probability of red given male here, we can basically use this formula to calculate that. So first we have to know probability of male and red, which is 0.3, and then probability of red, which is probability of red, which is 0.4. Therefore the probability of male given red, which is like 0.3 over 0.4, which is like 0.75, and the probability of male we know that, which is 0.5. So here you can see like the probability of male given red is not equal to probability of male, therefore it is not independent. So from this table you can say, for this table the probability of liking red and being male are not independent in that case for this table. So that's a all for today's lesson. I believe now you have good idea about what do you mean by independent or dependent events, and what are mutually exclusive events. And we have also discussed about different formulas, and I believe we'll be able to use the correct formula in the correct situation. And you should also be able to convert like the general English language to symbols, and from symbols to translate that in English.